Good day everyone, this is Module 10. Ang topic nato is still periodic motion, part 2. Let's go! So this is a balance wheel. Makita niyo sa image, pero this is a large version sa balance wheel. Usually makita ninyo sa kanang mga mechanical na mga clocks na wala beta mga battery, and it's designed to produce motion para kanang mag-create o kanang kumbeto kanang movement sa orasan. I'm not sure na po yata mga toys po nga na kinalang beta nimo i-rewind. Rewind ang yung spring, then move siya, but this one is like designed to give a very tiny na motion. So if you can design makontrol ang kanang motion niya slowly, then you can have something like this na pwede nimo magamit for like watches. Now, if we examine ang kaning balance wheel, you will see na ang iyang motion is angular, as shown here. So as it moves, di siya mo siya back and forth, but it's like clockwise and counterclockwise. Na siya, of course, na siya mo counter nga force. Not really a force, but another physical quantity na related po sa force. It's the restoring na torque, which we have discussed earlier sa mga previous na modules. So you put in yung review ang previous na module to check. So of course, na siya motion. So here we're gonna talk about ang relationship sa moment of inertia. So if you remember, inertia is like analogous to the mass. So the coil spring exerts a torque that is proportional to the angular displacement theta. So it's something like this. The torque is proportional to the angular position times a constant K. We call this one a torsion constant. Ang restoring torque is opposite ang iyang motion. So just like kanang restoring na force. So if we substitute this one to this expression, where K, so negative K theta is equal to I times alpha. Alpha is the angular acceleration. So if we try to expand this formula, we know that ang alpha, the angular acceleration, is the second derivative of the angular position with respect to time. And we can bring this one here and we can write an expression for this angular acceleration as a function of the torsion constant times the angular position theta over the moment of inertia. Now, if we compare ang linear o angular na simple harmonic motion, ang AX nimo the acceleration along linear behavior is given by the second derivative of x with respect to dt, and it is also expressed as negative k over m times x. K is the spring constant, and ang iyang angular frequency omega, which we derived earlier, is the square root of k over m. And from there, we note that omega is equal to 2 pi f, which is also equal to 2 pi over t. And if we rewrite that one, t is just equal to 2 pi over omega. So you have this function here. So this is, of course, 1 over omega. And ang period niya, which is period niya in relation to the frequency, is just 1 over the tau, the t. So 1 over 2 pi times the square root of km. Ang iyang counterpart sa angular, you have this. You have the angular acceleration, which we solved earlier, is equal to negative k over the moment of inertia times the angular position theta. So just by comparing the two, instead na spring constant k, we have the torsion constant na k pod. Instead na mass, you have the moment of inertia I. And we simply substitute this one to here, or 1 over omega, to get the period and the frequency. Okay, so let's go. Here we have two figures. One is ang they're both pendulum. They're both pendulum. Galing lang kani siya the second figure. The second figure here, the pendulum. Let's say na siya ay die, it would create a sinusoidal na function. Okay, it's going up and down, up and not up and down, like yeah, it's sort of up and down. It's a positive amplitude to the negative amplitude. Okay, so let's see ang kaning device is also what we call a pendulum bob. So simple pendulum. So as it moves, mag-create siya og sort of an arc length here. And you see here the restoring force. So the restoring force is being countered by the weight, specifically ang mg sine theta. So mg sine theta, ang iyahang one of its component, the other component is mg cosine theta. The restoring force is proportional to mg sine theta. But for a very infinite, not very infinite, but for a very small displacement, ang sine theta is equal to theta. So, if you look at here, if gamay kayo ang theta, meaning very small nga theta, ang sine theta is just around that. So, yeah. So, ang F restoring force is equal to negative mg sine theta if we're not going to use an approximate or a very small nga theta. Okay. Okay, let's proceed. So sine theta kani siya, if this is which one is the correct? Yeah, sine theta, this length here is also the length L. This one is the length X. Okay, so sine theta is equal to the opposite X over the hypotenuse L. So if sine theta is small enough, meaning, what does it mean? Ang imong theta small enough, like really small enough. So gamay kay siya. Say this is theta 1, theta 2 niya, gamay kay siya. Sine theta is just equal to, theta is equal to x over L. X over L. X over L siya. So the restoring force na instead na negative mg sine theta, this one is reduced to theta. So F restoring is just mg theta. So substituting x over L to here and combining the equations sa imuhang negative kx, which is the restoring force ni Muha, is equal to negative mg x over L. So the x cancels out. So ang imuhang spring constant is given as a function of mg over L. This is for a simple pendulum or a pendulum bob. Okay. Okay. Then of course, if we denote, if we recall ang angular frequency given by this one, and then ang k ni Muha mg over L, substitute here, you arrive to the angular frequency. This one cancels out ang imuhang masses. So imong angular frequency for a pendulum bob is given as a square root of g, the gravitational acceleration over the length L. Then the frequency, say naman din siya kay, is given by omega is equal to 2 pi f. So you simply divide omega by 2 pi and you get the frequency. And the frequency in relation to the period is 1 over f. So you have the period and the frequency. Okay. Okay. Next, you have a physical pendulum. So in a physical pendulum, you have you're composed of several na mga masses. So daghan kay na pendulum bob, but they are moving with the same angular na frequency. Okay? So if we denote this particular position here, although you have so many composition anania, you have the restoring torque is also proportional to mg sine theta. Again, we approximate sine theta close to theta. And again, you have here the length niya denoted as d. So this whole thing here is d. But for this case, this particular length with respect to theta is d. Okay, so that means sine theta is equal to the opposite, which is x over the hypotenuse d, and you arrive to what is that? mg d. That's mgd. So the restoring torque, which is equivalent to mg sine theta, is given by the function negative mgd sine theta. Okay. Now, since we approximate ang sine theta close to theta, so this term here, sine theta, is reduced to theta. The restoring torque now, if we equate this one, if you remember, the restoring torque is equivalent to the moment of inertia times alpha. So that's why we have this one here. So the restoring torque is equal to negative mg d, the length, not the derivative, is equal to I alpha. And alpha, angular acceleration, is the second derivative of theta. So equating this one here, so this one is, bring down nimo dire, so you have this one here. So d squared theta over dt squared is equal to mgd theta. So we then compare this linear equation for simple harmonic for acceleration. Comparing this, so if we remember, this one here for the curve motion compared to linear. So you sa ax nimo you have k over m times x. Sa imohang angular acceleration is mgd over I times theta. Okay, so if we let x equal to theta, we equate the 2k over m times theta is equal to mgd over I. Then we cancel out the theta, the angular position. So you are left with k over m is equal to mgd I. Okay, this value here, which we know, this is, if you take the square root of this one, you get the angular acceleration, square root of k over m. So if we take, that means this one is also equal to the angular acceleration, the square root niya, mgd over I. Okay, but take note, this is for not a pendulum bob, but a regular shape na mass. So we recall omega is equal to 2 pi f, and you divide this one by 2 pi, you get the frequency in terms of this angular acceleration, and 1 over f is just equal to the period. So you have this one. Okay. Let's look at this example. Let's say you have a uniform rod oscillating. So find the period. It's oscillating here. The center of gravity is positioned at L over 2. The length of the stick is 1 meter. For this case, the moment of inertia is not at the center of mass or center of gravity, but rather it is located somewhere here, the edge. So it's 1/3 ml squared. This is for a slender rod. Now, we recall the expression for the period. So we did not use a pendulum bob na expression, but we're using it for an arbitrary na shape niya. And for this case, it is a slender rod. So the period is equal to 2 pi square root the moment of inertia mgd. So the moment of inertia is given by 1/3 ml squared. Okay. Yeah. Actually, capital M. It doesn't matter. Okay, capital M ansad ni siya. And this cancels out ang masses. And this is simplified. Ang L diri cancels out with one of the L's there. And this one, ang 2 musako. So it becomes 2L over 3G square root of that one. So the period equation is given by this one. Substituting the value, so the period is around 1.64 seconds. Now let's compare the equations for the simple harmonic motion. This is for the linear simple harmonic motion. And this is for the angular simple harmonic motion. This is for the simple pendulum or the pendulum bob. And this is the physical pendulum simple harmonic motion. Okay. So they're all talking about the same thing. Nasa angular frequency, period, and frequency. Here, this is related to the spring constant K. This one is using the torsion constant, the angular simple harmonic motion. This is also related to angular simple harmonic motion, but this is for a pendulum bob or single na something like this na mag-rotate, mag-ana-ana lang siya. Okay, this is more general expressioning na diri. For a physical pendulum, it's something like this na mass dira and na siya point dira na mag-rotate. Okay, so depende sa problem, you can use any of the equations here, but you have to determine unsa ang gihatag sa problem. Is it a pendulum bob? Is it a linear motion na simple harmonic? Is it a physical pendulum? Okay. Notice mo klase, kani siya ang look at here, ang masses naga-change here na kay mass diri. This becomes moment of inertia. And this one here, wala siya moment of inertia, pero na siya length from the point of rotation padulong sa distance above. Here you go back sa moment of inertia. Okay. Kani gagamit siya torsion constant. Here it's using spring constant. So here we have a damp oscillation. So we see nag-oscillate siya. Look at here the damping. See what happens. So nasa gamay na damping. And as you can see, ang amplitude, the height niya ma-reach is not the same all throughout. But if you increase the damping, it appears na ang amplitude mo flatten siya. So it's acting like a sort of a friction. It goes against the motion, reducing the amplitude here. So here we have a mass attached to a spring. So it's allowed to oscillate. So on this area here na kay laylayang energy, you have the kinetic energy, the elastic energy due to the potential energy due to gravity, and the potential energy due to the elasticity. Let's examine one by one. So you have here ang kaning green ang kinetic energy. So as it moves, ang yung kinetic energy nagavary siya. Let's wait again. As it moves. Okay. Okay. As it increases height, ang potential energy kaning dark blue naga-increase. So as it moves pod ang mass nimo ha, naga-change ang iyahang kinetic energy. So when see, look at that. So pag mo paspas siya ang kinetic energy mo dako. Pag mo padulong na siya sa kanang murag muhine na siya, and then eventually mo stop before it changes direction, makita nimo mo gamay siya. Same of course, ang potential energy due to gravity na siya initial daan ako na given some height, I guess. Given some height here. So if you look at the changes, okay. Okay? So, ni taas siya, ni increase ang potential energy, ni abot siya sa ubos, but never stopping. But stopping at a certain height, ni baba po rin potential energy to gravity. Ang elastic potential, when mas stretch siya ayo, ang spring, mo increase po. Para pag mo abot siya sa kaning sa murag stable na position, kaning siya nga linya, look at it, mo zero siya. Okay? And another interesting thing is if i-increase ni moha ang damping niya. Increase ni mo ang damping niya. Look at this one. Okay. Because here you have the thermal energy. So if we increase katong una, ang condition is walay damping, sort of walay friction. But if you increase it, ang behavior sa imuhang mass spring kay mo decelerate. Look at it. Upon deceleration, because gi-counter siya by the friction. Look at this one here. So gi-increase. And if you see, ang iyahang thermal energy naga-increase po. So until eventually, ma-reduce siya then mo stop. Okay. So the mechanical energy is the sum of all the energies here will remain constant. Naga-vary-vary lang, naga-exchange lang ang kinetic to gravitational to elastic, then eventually reduced by the thermal energy, by the friction through damping niya. So, damp oscillation is the motion. Damping is the decrease in amplitude caused by a dissipative force. Okay, damping. Frictional damping is denoted by F is equal to negative BV, where B is a constant, and that describes the strength of the damping force. So the expression is the sum of forces is negative Kx, the spring-like behavior, minus BV. And if we allow it to move na siya motion, the sum of forces is equal to mass times acceleration. And substituting this one to here, you get negative Kx minus BB is equal to MA. And if we expand this one, this is negative Kx. Ang V nimo is the velocity, which is the first derivative of x with respect to time, is equal to the mass times the acceleration, the second derivative. So we put them on one side. So you get md squared x dt squared. Transpose, this becomes a positive. This also becomes a positive like this. The mathematical solution to this expanded form is given by this 10.43 and 10.44 for the angular frequency and the position x. So when when the angular frequency is 0 or the body reaches equilibrium, let's say omega is equal to omega naught, and we can simplify this expression. So B is equal to K spring constant times the mass. And if B is equal to this value here, if you substitute it back here, this result to the angular frequency 0. This is what we call critical damping. So wala kay, you can actually have three scenarios here. This is the first scenario, then you have the other scenario when B is greater than 2 times square root of km. So in critical damping, the system no longer oscillates and returns to equilibrium. Stop na siya. When B is greater than 2 square root of km, it's called overdamping. No oscillation but returns to equilibrium more slowly than critical damping. Eventually mo, abot na. The next one, when B is less than 2 square root of km, it's underdamping. The system oscillate and steadily decreasing in amplitude. Okay? So, nagkahinay lang siya, nagkahinay. Okay? But there's still oscillation. Nagkagamay lang siya. And that's it. So I hope you learned something new today. Ingat and God bless.